Hello friends, welcome to the next lecture of DES. In the previous lecture, we have seen about what the data encryption standard algorithm is. We have also seen that the working functionality of this data encryption standard depends upon the Feistel cipher itself, wherein the substitution and the permutation principles are used for converting the blocks of 64-bit into the ciphertext. That means the plain text block of 64 bits are getting converted into the ciphertext blocks of the same size 64 bits. Now, the DES algorithm has total 16 rounds, and in this lecture we will be learning what happens in every single round. So let's begin with it. This is the diagrammatic representation of the single round structure of the DES. Here you can see that if the 64-bit input is there, 64-bit input of a plain text block is then being divided into two halves, left and right, having 32 bits each. 32-bit right portion is then undergoing the expansion permutation. When it undergoes the expansion permutation, the 32 bits are then converted into the 48 bits. The output of the 48 bits, that is the expanded output, the permuted output, is then XORed. This XORing takes place with the help of the function key. The key here is again a type of the permuted key, because the key which is being used here is of 56-bit. Here you can see the 56 bits are also being partitioned into 28 bits, and then that 28 bits means the 56 size of the bit key is then converted into the 48 bit, and then these 48 bits of the key is XORed with the 48 bits of the expanded output. Once the XORing takes place, then the output of the XORed goes to the substitution box, that is the X box, and then the permutation process takes place, and the output of the permutation process, you can see the output of the permutation process is then XORed with the leftmost bit of your plain text block, and the output which we get at the end of this XORing then becomes the right part for your next round, and the rightmost bits before any functionality, they goes to the leftmost bit or the leftmost part to the next round. That means here the right portion is then becoming the left portion is then becoming the rightmost part for the second round, and the rightmost part is then becoming the leftmost part for the first round. This is the same structure as that of the Feistel cipher. The only difference here in the Feistel and the DES is the round, the functionality of the round. Every single round has to do this many functionality of the expansion of the key, permutation of the key, permutation of the bits of the plain text block, and then the XORed output then undergoes the substitution process, then the permutation process, and then how the XORed output of 48 bits is then again converted into 32 bits, because at the end, whatever the output we are getting at the end of the first round, it should be in the form of the 32 bits, because our original plain text block is of 64-bit, which is then divided into two halves of 32 each. So we'll see each and everything in detail. So the single round of DES, that means the complete DES algorithm uses 16 rounds. Each round of DES is a Feistel cipher. As I told you that it works upon the principle of the Feistel cipher itself. So you can see here the leftmost bit, rightmost bits, they are then undergoing the process of encryption where they are being where they are being mixed, and then the swapper, that is substitution with the help of the function key. That key is coming from this side. The key generation algorithm will then be used, which will then be converting your 56 bit of key into the 48 bit of size. Then the substitution takes place, and then the permutation, and then the swapping of the right shift and the left shift takes place. So this is the basic Feistel cipher which is used in the DES algorithm also. The heart of DES is the DES function, wherein we are using the 48 size of the key. The DES function applies 48-bit key to the rightmost bit to produce the 32-bit output. So, in the previous figure, we have seen that the two halves, that is the left half and the right half, out of these two halves, the right half is then undergoing the process of substitution to produce a 32-bit of output. So here what exactly happens is, when a 32-bit of input is given, which is nothing but the right portion of your plain text block, it then undergoes the expansion P box, that is the permutation takes place, which then provides you the 48 bits of output. Out of the 32 bits of input, it will give you the 48 bits of output. Whatever the 48 bits of output you are getting, that 48 bits of output is then getting XORed with the key. Now this key is the key generated for the round number 1, and therefore it is being mentioned here as the key 1, 48-bit size. Then whatever the XORing has takes place, the output is then given as the input to the S boxes. Here total 8 S boxes are used, and every S box performs its own functionality. We will see how the S boxes do their own functionalities, and then the output of the S boxes will again be giving you the 32 bits of the 32 bits, and then those 32 bits will again be undergoing the P box, that is the straight P box. Expansion P box, straight P box, they both are different. We will see in detail. And then the end of this function, we get the output of 32 bits only. This is the expansion P box. Since the rightmost part, that is the right portion of your plain text, is a 32-bit input, and K, that is the first key which is being generated for the first round, is a 48-bit key. We need to expand 32 bits into the 48 bits. So how the expansion permutation takes place? 32 bits are divided into 8 parts. 1, 2, 3, 4, 5, 6, 7, 8. And then before every first bit and after every fourth bit. That means before the first bit, 1 bit is added, after the fourth bit, 1 bit is added, and then it is swapped, as you can see here. So 32 bit is in this manner is getting converted into the 48 bit. This is the relationship, how it works. Like we have 32 bits, 1 to 32, okay, and then this 32 is added in the reverse order here. You can see 32, and then 4, then 8, then 12, 16, 20, 24, 28, and this first column is then added at the end, that is 0, 1, 29, 25, 21, 17, 13, 9 and 5. In this manner, the permutation takes place. Expansion permutation or expansion P box takes place, which then gives you the output of the 48 bits. That means the 32-bit right portion of the plain text block is then permuted to 48 bits, which will then be undergoing the XORing operation with the 48-bit key size. Okay, so after the expansion permutation, DES uses the XOR operation on the expanded right section and the round key. Note that both the right section and the key are 48 bits in length. Also, you should have a note that the round key is used only in this operation. That means only in the first round. The S boxes do the real mixing, that is nothing but the confusion. We have already seen the concept of the confusion and diffusion in the previous lecture. DES uses 8 S boxes, each with a 6-bit input, which produces the 4-bit of output. So how does the S box work? Total there are 8 S boxes, which has the 6-bit of input and produces the 4-bit of output. So 6-bit of input, 4-bit of output. Thus, out of the 8 S boxes, you do get a output of 32-bit, 4-bit each from one box. That is, every single box will give you the output as of 4-bit, which will combinedly give you the output of the 32-bit. In this way that the output comes, 6 bits are there, first and second bit is neglected, only the middle 4 bits are being taken as the output. This we have seen in the previous slide itself. There are a total of 8 S boxes, which then gives you the combined output of the 32 bits. Now this is the table which shows the permutation for the S box 1, and for rest of the boxes, or for the entries of the rest of the boxes, you can very well refer the textbook, wherein all the 8 S boxes entries are very well given in the book. Okay, so if we take the example that if any of the S box has the input of this 100011, so what the output your S box should give. Okay, so if we write the first and the 6th bit together, this 1 and 1, which will give you the binary, which will give you the decimal, in which we can consider it as a 3. The remaining bits we can consider as 0001, and which is nothing but the decimal 1. And for that thing, to get the output of this, what we will be doing is we will be seeing the 3rd row and the 1st column. So in the previous slide, if we see the 3rd row and the 1st column, and the intersection point is the 12. Okay, so it will give me the output as 12 in decimal, which is a bit in and how that 12 can be written in binary. It can be written as the 1100. So the input of the 6-bit gives you the output of the 4 bits. In the same manner, the remaining S boxes will also give you the output in the 4 bits. Now, this is the key generation figure, which tells you how the 56-bit of the key is then converted into 48-bit. So, key with parity bits, here they have considered as a, with the parity bits it is 64-bit, without the parity bits, that means when the parity bits are dropped, you can get the key of 56-bit, that is also called as the cipher key. 56 bits are then divided into 2 parts, that is 28 bits each, left shift and right shift. Then these 28 bits are compressed. That is also a type of a P box. Compression takes place, and when this compression is being taking place, the 56-bit size is then converted into the 48 bits. Here you can see the output here will then give you the 48 bits. For every round it will give the 48 bits. So for every round there will be a new key generated. Okay, that means round 1, round 2, round 3, 9, 16 others 1 bit, and for 1, 2, 9 and 16 1 bit shift is done, and for others 2 bit shifts are done. When you get the 48 bits of output, this 48 bit is then XORed with the 48 bits of the right shift of the plain text block, which we have seen in the previous figures. Again, then for the next key for which is required for the next round is then generated by using another shifts operation, compression operation, and so on, and till the 16th round the new keys are generated by implementing the same functionality of the compression pay box. Now here one point is to be noted is the key generation algorithm discards the each 8th bit and hence it compresses it. So out of 56, when it comes to 48, that means it discards total 8 bits. Every 8th bit it discards 8, 16, 24, 32, 40, 48, 56 and 64. It also includes the parity bits and therefore it is of 64 bit size. Now that was all about the encryption. We have seen how the encryption takes place. The right shift of the plain text block undergoes the XORing operation with the function round key, and then it undergoes the substitution process and then the permutation process. Permutation process takes place twice, before the substitution and after the substitution, and how we've seen then how the 32 bits are getting converted into the 32 bits are getting converted into 48 bit size of the plain text block. And then at the end, after the substitution takes place, at the end the 48 bits is again converted into the 32 bit size to get the ciphertext at the end of the encryption process. So after all the 16 rounds of the DES algorithm, we will be getting the ciphertext, which will also be in 32 bit size. Now how the decryption process takes place. Decrypt must unwind the steps of the data computation. With the Feistel design, we just have to perform the encryption steps again in the reverse order. So all the 16 rounds which are being performed for the encryption process of the DES algorithm, all those 16 rounds will then have to be performed in the reverse order for the decryption process. One point is to be noted that initial permutation undoes final steps of the encryptions. The first round with the 16th round undoes the 16th encryption round. 16th round with SK1 and undoes the first encrypt round. So that means if we are going in the reverse order, so 16th round output will undo the first encrypted round. That means whatever the output we are getting from the first encrypted round will then be producing the plain text of this 16th round, and then the final functions undoes the initial encryption process, thus recovering the original data value. That means in the reverse order, we will be then getting the decrypted form of the encrypted text which we got from every single round. This is a bit confusing, but just keep in mind that during the undoing of the encryption process, we will be getting the output. That means using the subkeys in the reverse orders, the subkey which is being used for the 16th round will then be using for the first round of the decryption process. Okay, these statements has the meaning like the subkeys which are being used for the 16th round of the encryption process undoes the first round of the decryption process. 16th round of the encryption process, undoes the first round of the decryption process, thus recovering the original data values. That means at the end of the 16th round of the decryption process, we will be getting our plain text back. Thank you guys. I hope you must have understood the single round structure of the DES algorithm. Guys, this is a bit complicated structure, but if you listen the lecture 2 3 times, you'll be definitely getting what I have explained in the single round structure of the DES algorithm. Thank you.